Hello, good evening. My name is Parth Joshi. So I am currently pursuing PhD in the Department of Mechanical Engineering at IIT Bombay, and I am also a recipient of the Prime Minister's Research Fellowship. And as a part of this, I got an opportunity through the PMR NPTEL team to conduct these tutorial sessions every week for this course on Introduction to Mechanical Vibration. So I would like to thank the NPTEL team for giving me this opportunity to conduct these sessions. So let us get started with the content for this week. So we are in the week 6. So till now we have dealt with different aspects of vibration. So like free vibration and uh, forced vibration and undamped and damped vibrations. We have also seen the concepts like vibration measuring instruments and uh, how they are designed based on their response. So the content for this week deals with two degree of freedom systems or in general multiple degree of freedom systems. So uh, so the basically the definition of degree of freedom is the basically that how many the number of degrees of freedom is the number of independent coordinates required to completely describe the behavior of the system. So that is called the degree of freedom. So when we need two coordinates to completely describe the behavior of the system, we call them as two degree of freedom systems. So the concepts covered in the content for this week are the undamped free vibration for these two degree of freedom systems. Then we also discussed about damped free vibration and forced vibration with harmonic excitation. So these are the concepts covered in the content for this week. So let us get started with the so let us try to solve some problems related to the content for this week. So let us get started with our first problem. So there is a system consisting of two spring mass systems, which is like two masses M1 and M2, which are suspended through springs K1 and K2 from the base, as shown in the figure. So, so the question is to find the natural frequencies of the system and with certain relations which are given in terms of M1, M2, K1, and K2. And also we have been asked how to determine the response of the system when K is 1000 Newton per meter and mass M is equal to 20 kg. So the initial conditions for the displacements of the masses, they are also given. So we have to find out the response of the system. So let us get started with this question. So the first thing about solving such problems is to define our coordinate system. So since it has already been given to us, what are the two coordinates? So we have the coordinates x1 and x2, which define the position of the masses m1 and m2. So let us say we have our coordinate system fixed over here to the base, and x1 and x2 are basically positions of the center of mass of m1 and m2 respectively with respect to their own equilibrium position. So we assume that x1 and x2 are given, are basically specified, measured with respect to the equilibrium position. So in that case, we do not need to consider the effect of the weights of the system. So the next step is then, once we have defined the coordinate system, our next step is to draw the free body diagram of the system. So let us consider the mass m1. So it has basically the force due to the spring K1. So that will be K1 x1, and the spring K2 is deformed because of the relative displacement between x1 and x2. So in our coordinate system, let us define that our x-axis is, let us say, vertically downward, and so therefore vertically downward is, let us say, positive. So let us assume that, for as a matter of, you know, to draw the free body diagram, let us to like assume that x2 is greater than x1, so that the spring K2 is also stretched. So the force acting will be also tensile, and it will be K2 into x2 minus x1. Similarly, the free body diagram for the mass m2. So it will have the force K2 into x2 minus x1 acting. So since we have assumed that x1 and x2 are with respect to the equilibrium position, then therefore we do not get any component because of the weight of the system. So we do not since we have assumed that x1 and x2 are with respect to the equilibrium position, the effect of the static deflection is being accounted for in the x1 and x2. So therefore, we do not have to consider any of the weights of the masses. So now the next step is to write down the equation of motion. So let us write down the equations of motion. So we will apply Newton's second law to these systems, and using our free body diagram, let us write down. So, so we will get minus K1 x1 plus K2 x2 minus x1 is equal to m1 x1 double dot, and similarly we will get minus K2 x2 minus x1 is equal to n2 x2 double dot. Now, if we want to rewrite this equation uh, in matrix form, so we can first let us first simplify these equations. Minus K2 x1 plus K2 x2 some problem with my screen sharing. So we can rewrite these equations now in matrix form. K1 plus K2 minus K2. So there is some problem with my screen sharing. I'm experiencing some problem with my screen sharing, so I'm not able to. There is some issue with my screen sharing in my tablet, so that's why I'm not able to screen share my screen properly. So we were basically trying to solve this equation in matrix form. So first, so first we have basically written down these two set of differential equations in matrix form. Now to solve this system of equations or system of differential equations, so let us assume. Uh, so let us call this matrix as Z, or so the matrix which is represented by x1 and x2, and the mass matrix as, let us say, this matrix as capital M, and the stiffness matrix which is this. So let us call them that as capital K. So we can write down this system in a more compact form as M Z double dot plus KZ is equal to 0 matrix. So to solve this system of equations, we will, let us say, assume a solution of the form Z is equal to V e to the power lambda t. To and then let us substitute this solution in the differential equation. So z double dot will be v. So we are assuming that v is a constant independent of time. So it will be lambda square into e to the power lambda t. So it will become lambda square m v e to the power lambda t plus k v e to the power lambda t is equal to 0 matrix. So we will get lambda square m plus k into v e to the power lambda t is equal to 0. So now this part e to the power lambda t is not equal to 0 for any real value of t, which is time. So for this system of equations to have a non-trivial solution, so the trivial solution would be the matrix v equal to 0, but we are not interested in that so trivial solution. So therefore we seek a non-trivial solution. So for that, this determinant of this matrix lambda square m plus k should be equal to 0. So therefore, uh, to get the values of lambda for which this determinant lambda square m plus k is equal to 0, so this will be our eigenvalue problem, or basically to find out the natural frequencies. So let us write down the value of this determinant. So it will be, this will be our mass matrix m1 m10 0 m2. So it will become lambda square m1 and the corresponding element in the k matrix is k1 plus k2. The second the element in the first row and second column for this mass matrix is 0, whereas the corresponding element in k matrix is minus k2. So it will become minus k2, and similarly the other non-diagonal element will be minus k2. So we observe that the mass and stiffness matrix are both symmetrical about the diagonal. So now if we solve for this equation, so we will get basically a equation in terms of, so it will be a fourth degree polynomial in terms of lambda. So it will have 4 roots of lambda. So for now let us substitute lambda square is some alpha, let us say. So we will get basically alpha m1 plus k1 plus k2 into alpha m2 plus k2 minus k2 square is equal to 0. So therefore we will get alpha square m1 m2 plus k1 plus k2 into m2 plus k2 into m1 alpha plus k1 plus k2 into k2 minus k2 square is equal to 0. Now if we want to simplify this equation further, let us divide both sides by m1 m2. So we will get alpha square plus k1 plus k2 by m1 plus k2 by m2 alpha plus k1 k2 upon m1 m2 is equal to 0. Now to solve this problem further, so we can put the relations between k by m, k and m uh, here itself, or we can also substitute it in a later stage. So the roots for alpha in terms of alpha would be let us call them as alpha 1 and alpha 2. So that it will be minus k1 plus k2 by m1 plus k2 by m2 plus or minus root of k1 plus k2 by m1 plus k2 by m2 whole square minus 4 k1 k2 upon m1 m2. 2. So we have been given that k1 is k and k2 is 2k and m1 is m and m2 is 2m. So we can put these relations over here. So it has been given that k1 is k, k2 is 2k, m1 is small m and m2 is 2m. So it is given. So we will put it in this equation. So we will get the roots as is equal to minus 3k by m plus k by m plus or minus 3k by m plus k by m whole square minus 4. So k1 by m1 will be k by m and k2 by m2 will also be k by m. So it will be k by m whole square upon 2, which will be minus 4 k by m plus or minus square root of 4 square to k by m whole square minus 4 into k by m whole square upon 2. So it will be minus 2 plus or minus root 3 k by m. So our natural frequency is lambda 1 square minus 2 plus root 3 lambda 2 square is equal to minus 2 minus root 3. So now we can see that the numbers minus 2 minus root 3 will be actually so it will actually be a negative number, so it will have two complex roots, whereas lambda 1 square is equal to minus 2 plus root 3, so it will also be a negative number. So therefore the roots lambda 1 1 lambda 1 2, so let us call lambda 1 1 will be root of lambda 1 square, and lambda 1 2 is minus root of lambda 1 square, and lambda 2 1. So you can see that these are complex conjugate pairs. So you will observe that they are all complex conjugates. So our natural frequency omega 1 square will be 2 minus root 3, or basically minus lambda 1 square, and omega 2 square will be 2 plus root 3, which is minus lambda 2 square. So those will be the two natural frequencies omega 1 and so omega 1 will be basically root of 2 minus root 3, and omega 2 will be root of 2 plus root 3. This is because why it is minus lambda 1 square, because we assumed the solution of the form e to the power lambda t, and lambda 1 square is actually negative. So this is equivalent to saying it is equivalent to assuming a form solution of the form e to the power j omega t. So where omega is the frequency. So therefore the lambda square. So minus lambda square will be equal to omega square in this case. So that's why we say that omega 1 square is minus lambda 1 square and omega 2 square is minus lambda 2 square. So since we assume the solution of the form e to the power lambda t, and so that's why we get the frequency as minus lambda square. Now to solve for the eigenvectors, or basically the eigenvectors corresponding to each of these roots, let us call v11, v12, v13, v21 or and v22 as the eigenvectors corresponding to each of these roots lambda 11, lambda 12. So each of these are, let us say, eigenvectors. Now to solve for these eigenvectors, we have to solve for the differential equation to find out the relation, so for the eigenvector. So let us assume that each of these eigenvectors, let us say Vij, is of the form V1 ij, V2 ij, so then we go back to our original set of differential equations. So what we got is our matrix was this lambda square m1 plus k1 plus k2 minus k2 minus k2 and lambda square m2 plus k2 this matrix into our vector v is equal to 0. So now let us try to solve for the eigenvectors. So therefore we will get lambda 11 square m1 plus k1 plus k2 minus k2 or if you want to generalize this, we can say lambda ij square m1 plus k1 plus k2 minus k2 minus k2 and lambda ij square m2 plus k2. So from the first equation what we will get that v2 is equal to into v1. So we can write down our eigenvector now in the form of, let us say, v ij will be, so v1 ij. So I can will be 1, 2, and j will be varying between 1 and 2. So we will get an eigenvector corresponding to each root lambda ij using this equation. So lambda 1 1 square will be again 2 minus 2 plus root 3, and so we can, in general, we can write our eigenvector. So let us say v11 will be v1 some constant, whatever constant it may be. So into lambda 1 square m1 plus k1 plus k2 upon k2. So which will be, so we can get this by substituting the value of lambda 1 square, and similarly we will get the eigenvector. So for v12 v21 v22 in a similar way. So let us say we have these four eigenvectors, v11, v12, v21, and v22. For each of these eigenvalues, lambda 11, lambda 12, lambda 21, and lambda 22 respectively. So what we can write that our response z is will be a combination of these eigenvectors plus So we can write the response as a combination of these eigenvectors and the eigenvalues in this way. So we can find out these constants C11, C12, C21 and C22 in terms of the initial conditions. So we can find out these constants using the initial conditions. So here we have been given that x1, x2 have been given as 1 and -1. So at time t equal to 0, x1 and x2 are 1 and -1 at t equal to 0. So by substituting these initial conditions, we can get the values of the unknown constants C11, C12, C21 and C22, and then we will basically get the final response of the system. So let us look at another example. So here we have been are similarly given two masses which are suspended through springs K1 and K2, and they are also attached connected together through dampers C1 and C2. And here we have a base to which the masses are fixed, but it can move, and the let us say we know the displacement of the base, and it is given as E of t, and the corresponding positions of the masses m1 and m2 are given by y1 and y2. So uh, let us start with this problem. So to derive the equations of the motion, we have to first define the coordinate system. So here it is already given that the coordinates of y1 and y2 are the coordinates of the center of masses of m1 and m2 with respect to their equilibrium position. So let us assume a coordinate system of this form where upward displacement is positive. So let's draw the free body diagram of the masses. So we will assume that y1, y2 are with respect to equilibrium position of the masses. So the spring force will be given by K1 y1 minus y2 because of the relative displacement, and C1 y1 dot minus y2 dot, and similarly for the mass m2 we will have another force due to the spring and damper. So it will be again k1 y1 minus y2 here now in the opposite direction, and c1 y1 dot minus y2 dot. Similarly, we will have the spring force because of the relative displacement between like y2 and e. So let us write down the differential equations for this system. So let us apply Newton's second law to the first mass m1. So it will be m1 y1 double dot is equal to minus k1 y1 minus y2 minus c1 y1 dot minus y2 dot. So all, since we are assuming the coordinate system in which our displacement is positive upwards, so that's why our forces are acting downwards, so therefore we have assumed the negative sign. Similarly for the mass m2, minus k2 y2 minus e minus c2 y2 dot minus e dot. So we can further simplify these questions. So m1 y1 double dot plus k1 y1 minus k1 y2 plus c1 y1 dot minus c1 y2 dot is equal to 0, and m2 y2 double dot plus or rather minus k1 y1 plus k1 plus k2 y2 plus C1 plus C2 Y2 dot minus C1 Y1 dot is equal to K2E plus C2E dot. So we can put this equation in a matrix form. Is equal to, it's actually equal to this. So let us write down this as matrix F. So where matrix F is so again I'm experiencing problems with my screen sharing. So we can write our matrix F as K0 and K2E plus C2E dot. So and if we write our mass matrix as capital M, which is M1 0 0 M2, and our stiffness matrix K will be K1 minus K1 minus K1 and K1 plus K2, and our damping matrix will be C1 minus C1 minus C1 and C1 plus C2. So let us write down our solution in matrix form. Let us write down our differential equation now in a slightly different form. So we will define our vector of y1, y2. Let us say we call it as the matrix. Let us say we call it as matrix Y. So we can write down our matrix as M. y double dot plus c y dot plus k y is equal to f. So now to solve this equation, we can assume a solution of the form, let us say y is equal to some vector v e to the power lambda t, similar to our earlier question. So then we can substitute this into the differential equation. So we will get y dot is lambda v e to the power lambda t, which is lambda y, and y double dot similarly is lambda square y. So therefore we will get lambda square m plus lambda c plus k vector into v e to the power lambda t is f. So here the solution, so this is a case of forced vibration. So the response will have two parts. One is because of the steady state transients, and other will be the steady state response, so which will be the uh, solution to the homogeneous. One part will be basically the transient part, so which will be the solution to lambda square m plus lambda c plus k into power into v e to the power lambda t is 0, 0 matrix. So that will be our solution to our homogeneous equation. So let us call it as YH, and the other will be basically the particular solution. Let us call it as YP, which will be so to solve this equation. So to find out the particular solution, we need to know the form of the forcing function, and depending on that, the particular solution will change. Now about the homogeneous solution, to have a non-trivial solution in terms of v, because e to the power lambda t anyway is not 0 for any real value of t. So therefore for non-trivial solution we need the determinant of lambda square m plus lambda c plus k is 0. So, to find out the natural frequencies of this system, we need to solve for this determinant. So it will be m1 into lambda square plus c1 lambda plus k1 and minus c1 lambda minus k1 and m2 lambda square plus c1 plus c2 lambda plus k1 plus k2. So basically determinant of this matrix is 0. So we will get the four roots which we call, let us say we'll call them as lambda 1 1, lambda 1 2, lambda 2 1 and lambda 2 2, similar to our previous question. So by solving for this determinant, we will get the four eigenvalues or four roots of lambda 1 1, lambda 1 2, and we will get the corresponding eigenvectors v11, v12, v21 and v22 or mode shapes in other words. So our response to the for the or basically the solution to our homogeneous equation will be combination of these linear combination of these eigenvectors and mode shapes. Basically the it will be a combination of these solutions plus C21 so this will be our general solution to our homogeneous differential equation. And let us say if our force is of sinusoidal nature, then we can assume our particular solution of the form of let us say a1 sine omega t plus b1 cos omega t and b2 sine omega t plus b2 cos omega t. So if the matrix F has some sinusoidal forces with frequency, forcing frequency of omega. So this may or may not be equal to the natural frequency, but based on that we can assume a particular solution of this form a1 sin omega 1 a1 sin omega t and b1 cos omega t. So basically combination of sine and cosine functions, and the YH will be basically our transient response. So our total response will be sum of the steady state and transient response. So we can get the values of C11, C12, C21 and C22 depend based on the initial conditions. Now here let us try to solve for our determinant. So it will be so m1 lambda square plus c1 lambda plus k1 into m2 lambda square plus c1 plus c2 lambda plus k1 plus k2 minus c1 lambda plus k1 whole square is equal to 0. So if we expand this expression or equation, so we will get m1 m2 lambda to the power 4 plus c1 into c1 plus c2 lambda square plus c1 m2 lambda cube plus c1 into k1 plus k2 lambda. Let me just write all these things on a new page. So m1 lambda square plus c1 lambda plus k1 into m2 lambda square plus c1 plus c2 lambda plus k1 plus k2 minus. So let us expand this equation. So we will get m1 m2 lambda to the power 4 plus m1 into c1 plus c2 lambda cube plus k1 plus k2 into m1 lambda square plus c1 m2 lambda cube plus c1 into c1 plus c2 lambda square plus c1 into k1 plus k2 into lambda plus k1 into k1 plus k2 plus k1 m2 into lambda square plus k1 into c1 plus c2. Lambda plus k1 into k1 plus k2 minus c1 square lambda square minus k1 square minus 2c1 k1 lambda is equal to 0. So we can slightly simplify these equations by dividing by m1 m2 throughout. So uh, or before that we can also try to uh, combine some of these expressions. So we will get m1 m2 lambda to the power 4 as it is plus. So let us try to combine the terms with for lambda cube. So it will be m1 into c1 plus c2 plus m2 c1 lambda cube. So those are the terms for lambda cube. Then the terms for lambda square will be k1 plus k2 m1 plus c1 into c1 plus c2 plus k1 into m2 minus c1 square lambda square. And then let us collect the terms of uh, which have the coefficients of the lambda uh, will be c1 into k1 plus k2 plus k1 to c1 plus c2 minus 2 c1 k1 lambda, and then the constant terms which are k1 into k1 plus k2. So it seems that we have this term. There was one term which was counted twice. So k1 into k1 plus k2 minus k1 square is equal to 0. So we will get m1 m2 lambda to the power 4 plus lambda cube plus k1 plus k2 m1 plus k1 m2 plus c1 c2 lambda square plus c1 k2 plus c2 k1 lambda plus k1 k2 is equal to 0. So this will be our characteristic equation, and it will have the four roots as I had mentioned: lambda 1 1, lambda 1 2, lambda 2 2, and lambda 2 1. And corresponding to each of these, uh, we will have roots. We will have a corresponding eigenvector. So how do we find out our eigenvector? Is to substitute our eigenvalue, each eigenvalue, let us say lambda ij, 2 lambda ij square plus c1 plus c2 lambda ij plus k1 plus k2 into p2. So this will be our ijth eigenvector. So for a non-trivial solution, we will get that v2 will be v1 of ij into m1 lambda ij whole square plus c1 lambda ij plus k1 upon c1 lambda ij plus k1. So where lambda ij are the eigenvalues, or where like ij can take the values 1 and 2. So these are the eigenvalues, and these are the. So how do we write the eigenvector now? So we can write it as, so the eigenvector ij, we can write it as v1 and so this will be our eigenvector corresponding to each eigenvalue lambda ij, and then our response will be a linear combination of our eigenvectors. So this is how we can write our response in terms of our eigenvectors as a combination of the response due to each of these solutions, combination of the solutions in terms of the eigenvectors v11, v12, v21, and v22. So these are our. So now let us look at an example of how we can solve such problems using MATLAB. So we will see a version of how this problem, where we have a system of this same form, and this can also be called as a quarter car model, where we model the motion of a car, uh, or basically we model the car, and so when the car goes over a bump, to find out what will be the response of the car body and the wheels to such kind of a bump. So if the road is bumpy, that like the car body will go up and down, the wheels will also go up and down, and so there is a role of the suspension over here to play. So let us go to our example in MATLAB. So let us go to MATLAB and see how we can solve such problems using using this concept. So let us go to our quarter car model. So here we can model our passenger car using the same system, which is as a 2 degree of freedom system. So here we assume that our whole car body, along with passengers, let us say it is modeled as the mass m1, and the suspension, it is modeled as a spring with stiffness k1 and damping coefficient c1, and then the tires together are modeled like as a single mass m2. So let us say there are four wheels, so all the four wheels together as modeled as the mass m2, and then the stiffness of the tires together, that is modeled as a spring of stiffness k2 and damper with damping coefficient c2, and this tire is in contact with the road. So let us say the road profile is given by the function e of t. So in we will try to see how we can use MATLAB to solve this the response of this system. Uh, we will run this. So we here there are some assumed values of the masses m1, m2, k1, and k2, c1, and c2. So these values have been suitably assumed so that should approximately represent the behavior of a car. So we will simulate uh, if there is a sinusoidal excitation of this base or E of t. Let us say that the car goes over a bumpy road where the profile of the road is like sinusoidal, and then so that is equivalent to a sinusoidal base excitation. So now the role of our suspension will be to ensure that the magnitude of the or the amplitude of the displacement of the mass m1 or the car body should be as small as possible. So the passenger should not feel too much of the bump here. So then therefore the value of y1 should be as small as possible. So therefore we have chosen a spring k1 which is slightly less stiff as compared to the tire stiffness K2, so which is an order of magnitude lesser than uh, K2. So K1 is almost 10 times lesser than K2. So let us see how we can use MATLAB to solve this problem. So in MATLAB, I have this the code. So let us say we will look at our sample code. So here we have entered the all the specifications mass like the masses and the stiffnesses, and and we have also given the time interval over here. We are also assuming that initial conditions are z naught, which is basically the initial displacement of the masses m1 and m2 to be 0, and also the initial velocity of the masses M1 and M2 is also 0. So we give an excitation of frequency approximately like 1 hertz with a amplitude of zero point 0.1 meters, which is approximately 10 centimeters. So it's near about the same order of magnitude of speed breaker that a car would encounter. So let us say the road profile is such that it's like a sinusoidal road which has multiple such speed breakers, one after the other, and the profile is approximately sinusoidal. So in this part of the code, we in we are giving the we are basically trying to solve the system. We are representing our system dynamics in MATLAB. So we enter the mass matrix, stiffness matrix, and damping matrix, and also the external force matrix. So here we have assumed the excitation E of t as sinusoidal. So here in this part we are basically trying to solve the uh, determinant of the matrix lambda square m plus k plus c lambda plus k is 0. So it is basically the determinant of lambda square m plus lambda c plus k equal to 0. So we can construct it and represent it as a polynomial in terms of these, and so these are the coefficients. So now to find out the roots of this equation, we use the function roots, and so as we know that we will have four roots, so these will be the four roots of the characteristic equation. And now if we turn to our particular solution, we will get this particular solution by assuming the solution of the form the particular solution is assumed to be of the form a1 into sine omega into t, where we are assuming that the uh, particular solution is the force is sinusoidal, so that we are assuming a sinusoidal function to approximate to solve for the steady state response, and we are assuming that the force is acting at a frequency of omega. And if we substitute this particular solution in our differential equation, we will get our uh, coefficient matrix AP, and that we can use it to solve for the coefficients a1, a1, a2, b1, b2. So this is the part of the code where we calculate a1, b1, a2, b2, and then in this part we calculate the eigenvectors in terms of the roots r11, r12, and r21 and r22. And here we also calculate the eigenvectors, and then we here in this part we apply the initial conditions. So we know that this is the initial displacement initial condition and velocity initial condition. So Zp naught is the uh, initial displacement and initial velocity of this particular solution that we have assumed, and so we and b is the total uh, coefficient matrix for the transient solution. So we can solve for these unknown constants C11, C12, C21, and C22 as we can see over here using this initial conditions, and then we get the total response as the sum of the uh, solution to our homogeneous differential equation and the particular solution. And here we plot the solution in this form. So let us try to run this code. So now as we can see over here, the blue curve represents the displacement of the car body, which is m1, and the m2 is the displacement of the tires or wheels. So we can see that because of the values of the damping that we have assumed, the system settles down fairly quickly. So the transients are not seen beyond, let us say, time 2 or 3 seconds. So if we can actually zoom into this part of the graph. So we can see that our transient part is present in the initial 2 or 3 seconds of the motion, and beyond that it's mainly the particular solution or the forced vibration that takes over, and that is the steady state response. So we can see that the amplitude of the or the magnitude of the displacement of the car body is much smaller than the actually the displacement of the mass m2. So so we can see that our suspension values that we have chosen, they seem to have to um, whatever the values that we have assumed, they seem to satisfy our equations properly. So this has been plotted in mm. So the displacements of the car body, it's about 25 mm in the steady state, which is 25 mm is not a very big displacement. So on the other hand, our wheels actually go through a larger displacement of about 100 mm or so, which is about 10 centimeters. So we assume the height of the speed breaker to be about 10 centimeters. So in comparison to that, the displacement of the car body is only 2.5 centimeters. So it is significantly reduced because of the suspension. So we can also similarly represent our plot by assuming an initial condition. Let us say we assume this initial condition of this. So let us say if we assume that there is no excitation and we apply some initial condition of velocity, so then we are able to replicate this response. So we see that our car body over here. So when we give a velocity boundary condition to the wheels, so then we can see that because of the damping present in the system, the amplitude is decaying, uh, and so because of the damping present, as well as the because of the suspensions stiffness and damping present, we can see that our uh, car body does not move as much as our wheels. So the suspension is seems to be operating or working well in this case. So we can see that uh, by applying these kind of different initial conditions, we can see how the system behaves. Let us say now if we apply a velocity initial condition to the car body, then we can see that this the car body now moves more than the wheels. Again we get a similar case like when we apply a initial condition of displacement of zero point 0.1 uh, zero point 0.1 meters to the wheels, let us say, then we see that our car body, the motion of our car body will be small, but it will eventually decay very fast. So because the damping that we have assumed for the wheels, so it is uh, the damping C1 value is actually very high. So that's why our system takes significant amount of time to for the amplitude of the car body to decay to zero, whereas with C2 the time required to reach the equilibrium position is lesser, although there are more oscillations. Uh, so we can see how the damping affects the behavior of our system. So here we can see that the blue curve, it takes a long time to reach the equilibrium position of zero, whereas the uh, red curve actually returns to the equilibrium position slightly faster than the blue curve. So the damping value is lesser in case of the red curve. Uh, it's almost about 5 times lesser. So although there are more oscillations, the system returns to the equilibrium position slightly faster. Whereas here, in case of the blue curve, the motion itself is sluggish. So basically, the uh, what the damper does is that it makes the motion of the car slightly sluggish. So we can also use MATLAB to create an animation. So let us have a look at an animation of this motion. So in this case, our base is subjected to a sinusoidal excitation, whereas so we can see that the lower mass, which is the wheels, which represents the wheels, it is moving much more than the upper mass, which represents the car body. So you can see that the suspension system is performing quite well in this case. So the amplitude of the movement of the car body is much smaller. So this is how we can use MATLAB to create different animations or use it for different calculations in which we can uh, solve the differential equations in for these vibrations. So it's a very useful tool, and you can also use it to create such animations. So I hope this today's session was useful. Uh, so let us meet in the problem solving session for the next week on Monday. So we will stop here for today. Thank you.